Hey everybody, let's start working some simple harmonic motion sample problems. Here we have a mass on the end of a spring. We have a 5 kilogram mass, spring with a spring constant. So I'm going to write that down, spring constant, and this is the mass. And then this mass is going to be oscillating back and forth between these two extremes. So this is our equilibrium point, and this is the amplitude. It's going to be oscillating back and forth between these 2 points. Now right here the forces all cancel out. That's what the equilibrium point means. So while we're on the idea of forces, let's just draw our free body diagram here when it's at the equilibrium position in the middle when the spring isn't stretched. Okay, when it's sitting there, we should have a gravity force down, which we'll label mg. Remember to go to one of these lines with your arrow. And then we should have a normal force up, and those two should be the same. They should cancel, and there's no spring force because we're at the EQ, equilibrium point. The sum of the forces add up to 0. Now, when we're out here at the end at 0.2 meters, okay, we should have the exact same gravity force and normal force. So there's our normal. There's our gravity force. Oops, I named it Fg this time. Doesn't really matter. They're still the same. And we'll have a spring force to the left. Force spring. Make sure you label it properly. We don't know the relative size of the spring force compared to the others yet. With the information that's given, we could probably find it. Okay, so now let's talk about the motion. So this is the equilibrium position. Here's our maximum amplitudes. We know that the velocity out here is 0, and we also know that in here the velocity is a maximum. So it stops at the end, speeds up, fastest here, slows down, turns around, and repeats. We also know when it's all the way out, it has its maximum spring force. So this is where the acceleration will be maximum, but it will be to the left when the amplitude is to the right. And we know we'll have our max negative acceleration, or I'm sorry, to the right when this is to the left, and that our acceleration equals 0 in the center because all the forces cancel out. We're in equilibrium. So let's just go ahead and write that down. The forces equal 0 here, and we have our max force, max force to the left here, and we have our max force to the right here. All right, so there's our motion ideas, how it goes back and forth and back and forth. Let's talk about the energy now. So in the middle, it has its maximum velocity. So the kinetic energy should be a maximum in the center, and the kinetic energy should be 0 on the ends where it stopped. Conversely, we'll have our maximum spring potential energy on the ends, because that's where, remember, this is 1/2 kx squared. This is 1/2 mv squared. And this is where we have our maximum displacement, so we should have our maximum potential energy on the ends, and we should have 0 potential energy in the middle. So if we were to graph this, say from here to here, from 0.2 meters to negative 0.2 meters, and here's the equilibrium spot, and we graphed, say, energy, then the potential energy would look like a parabola here. That would be the spring potential, because it's 1/2 kx squared. It's proportional to x squared, and this is x. Our kinetic would be just the opposite, like this. There's our kinetic, because it's maximum in the middle, 0 on the ends. And if we add those two up, this should be our total energy, which equals kinetic plus potential. And that should be constant the whole time. Let's calculate or see what we can calculate with this idea of energy. So we have spring potential energy equals 1/2 kx squared, and we have 1/2. We know that k is 30 newtons per meter, and x maximum at least is 0.2 meters. And if we plug that in our calculator, my calculator said 0.6 joules. Now, always check my numbers. You've seen me in class, and you know I make mistakes just like everybody else. So always check, just in case I've made a mistake. So this is our maximum potential. So that's when we're at the amplitudes. That means that should be the exact same as our kinetic maximum. So that should also equal 0.6 joules when we're at equilibrium. And if we put down 1/2 mv squared, we can find the maximum velocity. And if we plug in our numbers of 5 kilograms, we can calculate the velocity, and I got 0.49 meters per second for my maximum velocity. I should write that down. Let's see, what else can we find? Let's see. Well, let's look at forces. Go back to forces again, find out what this force was. So that maximum spring force would occur when we're at the max amplitude, because Kx is our equation for the spring force. And so if we plug in our spring constant, which is 30 newtons per meter and 0.2 meters, we get a maximum force of 6 newtons. Since F equals ma, we can find out what this maximum acceleration would be then with our maximum force when we're at the maximum amplitude, and that would just be this force here and then the mass of 5 kilograms, and if we plug all that stuff in, we'll get an acceleration of 1.2 meters per second squared. Is there anything else at all to find? Well, actually, yes. We can look at the time period now. So let's move this up just a touch. So the time period for a spring mass system is 2 pi square root of m over k. If we plug in our values from up top with our mass of 5 kilograms and our spring constant of 30 newtons per meter, we will get a time period of about 2.6 seconds. Now, that also means that the frequency of the motion is 1 over the time period, and then that will be 0.39 hertz. Okay, so there's our frequency, there's our time period. Remember, the time period for a spring is proportional to the square root of m. So if we would quadruple the mass, we would double the time period. So if we quadruple this, the square root of 4 would give us 2. But the time period for a spring mass system is proportional to 1 over the square root of the spring constant. So if we would increase the spring constant by 9 times, then that means this would be divided by the square root of 9, which would be the time period would be 1/3 of the original. All right? So there's a ton of information we can find from this one problem. Now let's take a look at a pendulum. So here's a pendulum. It's swinging back and forth. It starts, say, at A, and it swings down through B, the lowest point, and comes back up to C. So first off, let's take a look at the kinematics of what's going on. Remember that the velocity at the bottom will be a maximum, either going to the right or left, depending on which way it's going. That the velocity at the ends will equal 0, where its displacement is maximum, the velocity is 0. And then remember that at the ends, the acceleration is a maximum this way towards the equilibrium. This is the equilibrium position. And so therefore the acceleration equals 0 here at equilibrium in the center. And then down here we have an acceleration which equals a maximum again, but this time it's in that direction instead of this direction. Let's see, what else can we know? Let's take a look at the force situation of what's going on. Let's call this position A and this one here position B. What will our free body diagrams look like at both spots? So here at A, we're going to have a gravity force down, and that's a pretty crappy arrow, but there's my gravity force down, mg, and then we're going to have a tension up this direction. Now, I'm going to draw mine up like this, tension. Now, if we really take a close look at this, there's going to be a component like this, and this component here will cancel this component so that we have only this component right here. And if this is theta, this is theta, and this would be mg sine theta, and that would be the part right here making it accelerate this way, tangent to the path on its way back towards equilibrium. Okay, So at the ends, we have an acceleration back along the pathway towards equilibrium. Now, if we look at point B over here, then we're at the bottom. We should have the same gravitational force. So here's an mg force down, but we here are moving through an arc, okay? So therefore we must have a centripetal acceleration. So the force upward here, tension, has to be larger than mg. So tension is greater than mg here, but over here on the ends, mg is greater than the tension because we have extra mg left over to make it accelerate back towards equilibrium. Where here, we have a centripetal acceleration upward. So right here, we're accelerating upward with a centripetal where these are tangential. Okay, that's actually really complicated. All right, so now let's take a look. We've looked at the kinematics, we've looked at forces. Let's look at the energy situation. And so here at the ends, let me do this in a different color. Here at the ends, this will be gravitational potential energy, and here at the bottom, we'll have kinetic energy, where this is maximum, all potential in the end because it's stopped, all kinetic here because I'm going to call this point right here our y equals 0. And so our height that we're using is this height. That's our delta y for our gravitational potential, which is mg delta y. Now, how do we get this delta y? Remember we did this in class, and it's a little complicated, so let's go through it again, because it's easy to forget. So here we can draw a triangle right here, where the triangle, this is the length of the string from here to here. So I'm going to mark that one in blue. You can see it in blue. This side over here is going to be, there's theta. This is going to be the L cosine theta side from here to here. So this little bit from here to here is the difference between these two, because this is L from top to bottom, and this is L cosine theta from here to here. So if we do that, what we'll end up with is that this delta y equals L minus L cosine theta. Our gravitational force, I'm sorry, not a gravitational force, our gravitational potential energy will be mg L minus L cosine theta. All right? Okay, what will our kinetic energy be? Well, sorry, this is the maximum, right, at the end. And our maximum here must equal our maximum here, right? They must be equal. So at the bottom, our kinetic energy is a maximum, and it has to equal this gravitational potential energy maximum here at the top. So once we find this, we can plug that in here, and since that equals 1/2 mv squared, and if we know the mass of this object, we can find the velocity of the object at the bottom. All right? So what about time period? So this is a pendulum. So time period for a pendulum is different than time period for a spring. It's 2 pi square root of L over G. I want you to notice right off that the mass doesn't matter. So if we double or triple this mass, we don't care. It's got the same time period. Also notice that theta doesn't matter. Just like in our spring problem from before, the amplitude didn't matter. How far it swings back and forth on that spring doesn't matter. The amplitude theta here doesn't matter either. Our time period is not proportional to the mass. Our time period is proportional to the square root of L, and our time period is proportional to 1 over the square root of G. That means if we go to the moon, where G is smaller, if G gets smaller, time period gets bigger, and so the time period of a pendulum would be longer, so it would swing back and forth slower on the moon. If we change the length, say like if we quadruple the length, make it 4 times bigger, then the square root of 4 would be, we have twice the time period. All right? And there's the basics of simple harmonic motion for a pendulum. Just in case we see one of these on the test, let's look at a vertical spring mass system that oscillates up and down. We have 3 energies going on in this problem. So if we take a look at this one, here is the original length of the spring. And then if we put a mass on it, then there will be a downward force of gravity and there will be an upward spring force, which is kx, in this case delta x, since it's stretched delta x. This is our equilibrium position right here. EQ right here. Okay? These two must be equal at the equilibrium position. Now, if the disembodied hand of science brings it down another delta x, this will be our amplitude, and it will oscillate up and down, back and forth between here, the equilibrium, and the amplitude at the top. Let's take a look at what's going on with the energy here. So if we call this y equals 0, then we will have 0 gravitational potential energy here at the bottom. And then at the top, we will have our maximum gravitational potential energy, which will equal mg delta y, but our delta y will be 2 delta x, because it'll move from here through delta x and delta x before it stops at the top. If we look at our spring potential energy, I've run out of room here. Our spring potential energy at the top equals 0 because that's where the original length of the spring was, and so there's no stretch at all. So our spring potential maximum will be at the bottom, which will be 1/2 kx squared. But for us, that maximum will be 1/2 k, and then our stretch is going to be 2 delta x squared. What about kinetic energy? Well, the kinetic energy is going to be equal to 0 on the ends because it'll have to stop. By the way, that's a capital K, not a small k. So it'll have to be 0 at the top and the bottom because it has to stop. So it means its maximum is always at the equilibrium. So the maximum, which equals 1/2 mv squared, is in the middle. Let's put this all together. So when we're at the top, and then here's the bottom, and here's the equilibrium position. When we're at the top, we're at an amplitude. And we're at the bottom, we're at the other amplitude. And so at the bottom amplitude, we have maximum spring potential energy. When we're at the top, we have maximum gravitational potential energy. And everything else is 0. So we have 0 kinetic on the ends, and we have 0 spring at the top, 0 gravitational at the bottom. So in the middle, we have all three. We have our kinetic energy maximum, but we have some gravitational, and we have some spring. Okay? And all three of these must be equal to the conservation of energy, as long as we don't have any losses. So energy as a function of time should look like this, and the others should be oscillating in between here. Now, if there's, say, drag, or there's some frictional losses in the spring, then what will happen is this maximum value will decay over time. Okay, and then all these energies will be oscillating around underneath that envelope. The College Board loves to put multiple parts of physics together in one problem because they're trying to see if you really understand what's going on by mixing it up. So here's one where we have colliding objects with a spring. All right, how do I know this is going to be a momentum problem, and how do I know it's going to be a simple harmonic motion problem? Well, because the objects are going to collide. Anytime we have colliding objects, conservation momentum is in play if we can include all the objects that are interacting. And then because they're going to hit, stick, and then oscillate, we'll have simple harmonic motion physics in play. So let's start with the initial conditions. In the initial condition over here, the initial momentum is mv, and that's going to turn out to be 0.6 kilogram meters per second. All we have to do is multiply these two numbers together. Let's also find the initial kinetic energy, which is 1/2 mv squared. If we plug these numbers in here, surprisingly, we get the same number, but they're not the same because they have different units. This is in joules. When they hit, they're going to do this. They're going to collide, and the immediate reaction afterwards is we're going to have motion with these two stuck together. This is a perfectly inelastic collision, which means energy is lost. So let's take a look at our final momentum. Well, it must equal our initial momentum because it's a collision and we're including both of the objects interacting. So our final momentum is going to be the same as it was at the start. But our energy will not be the same because remember we lose kinetic energy whenever we have an inelastic collision. So let's find our final kinetic energy, which will be 1/2 mv squared. Now be careful, this is 1/2 m plus m, the two masses together, times our final velocity, which I don't know what it is yet. So let's find out. So let's go back to momentum. This final momentum must equal m plus m times v final. And that's the mass of both of them together. So it's 1.3 v final. So our final velocity turns out to be 0.46 meters per second. And I'm running out of room. There's our final velocity. So I'm going to plug that in here for our velocity. And so I get 1/2, our mass is 1.3 kilograms, and our velocity 0.46 squared. So our final kinetic energy turns out to be 1.14 joules. Now notice how the final momentum is less than the initial momentum because this is an inelastic collision. All right, what else can we find out? Well, when these two collide, this thing is going to compress back this way. How far will it compress? Well, if we think about it, we have an object here on the end of a spring. It has kinetic energy at the equilibrium position, and that's where the kinetic energy is a maximum. This is our kinetic energy. When they hit and stick and collide, that's the initial energy of the spring mass system. So the kinetic energy it has here must equal, when the spring is all smashed up, the spring potential energy here. So the spring potential energy equals the kinetic energy maximum, and this is 1/2 kx squared. So I get 0.14 joules equals 1/2 100 Newton per meter. Solve for x squared. So our maximum compression will equal 0.053 meters. Is there anything else we can figure out about this? Well, it's an oscillating object, so we could figure out the time period. The time period for a spring mass system is 2 pi square root of m over k. Be careful, that's 2 pi square root of the mass that's oscillating, which is the whole thing. So 1.3 kilograms over 100 newtons per meter. So our time period turns out to be 0.72 seconds. And that's it.